If you want an AI to generate a really detailed, complex image, common sense dictates you should give it a more detailed prompt. Write a huge paragraph.
Right, like describe the lighting, the mood, the exact placement of every single object.
Exactly. But what if I told you that adding more words actually makes state-of-the-art diffusion models perform worse? Welcome to AI Paperslop, the YouTube series where we summarize AI and tech papers for technical folks who need to stay on the bleeding edge.
No fluff, just the signal.
Yeah, and today we are tearing into a mind-blowing paper titled Scaling Properties of Text Conditioning in Visual Generation by Zilong Chen and a team of researchers at ByteDance.
And we're just jumping straight into the core insight here because it totally upends how the industry approaches prompt engineering. So here's the TLDR.
Lay it on us.
Naively making natural language prompts longer does not improve text-to-image generation. Actually, it actively degrades performance in top-tier models like FLUX.1 and EMUC.
Wait, really? It degrades it?
Yes. The researchers mathematically prove that the models are starved for information, not token count. So by abandoning prose and converting text conditioning into JSON-like structured prompts.
Structured prompts.
Yeah, SPS. And then by measuring image-grounded information using two brand new metrics, Grounded Perplexity Gain and Effective Detailness, they discovered a mathematical scaling law for text conditioning.
Which is huge. And they then trained an LLM to act as a translator between users and the diffuser, right?
Exactly. And that resulted in an end-to-end system that beats almost every open-weight model on compositional and reasoning benchmarks.
Okay, so the mission for this deep dive is packed. We're going to deconstruct these scaling laws, look at the exact architecture of the structured JSON prompts, and break down the fine-tuning pipeline used to train the LLM prompter.
Sounds good.
But first, we just established that adding more words doesn't work. Let's look at the experimental proof of why natural language stalls out. The researchers call this a fixed backbone reconstruction probe.
Right, and the setup for that probe is highly controlled. They took a single held-out reference image, so a really dense, complex photograph with multiple subjects.
Lots of intricate background details, that kind of thing.
Yeah, and they wrote natural language captions for it at increasing lengths, starting from a standard description of about 470 tokens and progressively scaling it up to over 2,100 tokens.
Okay, so they passed these increasingly long prose captions to a frozen Qwen-Image backbone, basically to see if a massive word count translated into a better reconstruction of that original image.
Exactly. The assumption being, if I give the model 2,000 words exhaustively describing a scene, the attention mechanisms in the text encoder should extract a near-perfect replica, right?
Right. Compared to a brief 400-word prompt, it should be way better. But it wasn't. The data shows a total failure of that assumption. The reconstruction quality remained completely flat.
Flat as a board. Adding more prose didn't help the diffuser at all. And the mechanism behind that failure is what really matters here.
Right, because adding more words in natural language usually just means elaborating on the same entities,
Yeah, exactly. You're layering adjectives describing the philosophical mood of the scene, but you aren't exposing new, concrete visual variables for the diffuser to latch onto.
It's like you're giving a police sketch artist a 10-page essay on the psychological aura of a suspect, rather than just giving them the exact dimensional coordinates of a scar on their left cheek.
That is a perfect analogy. Verbosity is not visibility. If you bury the spatial data in a sea of adjectives, the text encoder just averages out the semantic meaning.
It just deletes it.
Exactly, the dilution effect. And the researchers proved this wasn't just a quirk of Qwen-Image. They ran this test across Hunyuan 3.0, Bagel, FLUX.1, Dev, and EMU3.
Every single open-weight model, basically.
Yeah, and every single one hit an early ceiling. They all actually ended up performing worse with the 2,100 token prompt than they did with their shortest caption.
Wow. I mean, some models like FLUX.1 Dev just truncate the text encoder past 512 tokens anyway, right?
Right, to avoid this exact noise. So if natural language actively confuses the text encoder, we have to completely change the language we speak to the model.
We need a format that forces the model to learn distinct visual variables. And the researchers call this concept diffusability.
Yeah, diffusability. To maximize it, the ByteDance team abandoned natural language entirely and introduced the structured prompt, or SP schema.
Which is basically a giant JSON file.
Pretty much. It's a strict, syntax-heavy JSON schema that forces visual variables into explicit typed fields across 3 scopes.
Okay, let's break down those scopes. So first, we have the global scope. This is things like the intent, the scene setting and atmosphere, photography style, and lighting.
Right. Then, one level deeper, you have the per element scope. This schema allows for up to 20 distinct foreground elements.
20, that's a lot of detail.
Yeah, and every single one gets a unique ID, a specific caption, attributes, a really precise bounding box, and an explicit depth value from 0 to 255.
Oh, that depth value is so cool. It acts exactly like a z-index in web development, just definitively telling the model what sits in front of what.
Exactly. And because every element has an ID and a bounding box, the JSON can move to the third scope, cross-element relationships.
Right, explicit relationships, like semantic support, physical interaction, or bounding box overlaps. It leaves nothing to the text encoder's imagination.
It completely bypasses the ambiguity of human language. In a huge sentence, the encoder might blur the binding between an adjective and a noun, but a JSON key value pair is absolute.
Right, element 5, color, red, there's no linguistic ambiguity there.
Not at all.
But wait, how did they even get this training data? They obviously didn't have human labelers handwriting 1,300 token JSON files for millions of images.
No. They built an automated annotation pipeline. They paired a vision language model, a VLM, with a bunch of frozen domain experts.
Yeah. Okay, what kind of experts?
So they use Sapiens for human pose data, depth anything v2 for the relative depth, and SAM 2.1 to generate masks and handle occlusion logic for the bounding boxes.
So the VLM just acts as the orchestrator, taking all these geometric inputs and formatting them into the SPJSON.
Exactly. And when they applied this new SP schema to that reconstruction probe where prose failed, the metrics didn't just improve, they skyrocketed.
They tracked it with DynoV3 for semantic matching, SIGLIP2 for text-image alignment, and LPIPS for perceptual visual matching.
Yeah. And as they added more field groups to the SP, like starting with bounding boxes, then background, then dynamic attributes, then depth, the reconstruction quality improved steadily at every step.
So unlike the natural language test, there was no plateau at all.
None. The more structured info they provided, the better the model performed.
Okay. Seeing a qualitative improvement on a probe is awesome. But this paper actually mathematically proves why this works, right? Which means we have to measure information.
Yeah, which sounds super abstract, but they formalized it beautifully using two new metrics, GPG and ED.
So GPG is Grounded Perplexity Gain. They call it a white box metric, basically measuring token-wise grounding gain.
Right. Think of it like this. You give a frozen VLM a standard text caption and ask for the likelihood of those words. Then you reveal the paired image.
Okay.
GPG measures how much revealing that image raises the caption's likelihood. If it's just flowery prose, the image doesn't add much certainty.
But if it's explicit JSON coordinates, revealing the image causes a massive spike in likelihood. That spike is the Grounded Perplexity Gain.
Exactly. Now, the second metric is ED, Effective Detailness, which is their black box metric. For this one, they use Gemini 3 Pro.
Treating it like a database parser.
Yeah, Gemini extracts object attribute relationship tuples from the image, like man wearing watch, watch color silver.
So it builds a factual database from the image and then checks the precision and recall of the caption against those tuples. It's just a pure fact-checking metric.
Exactly. Now, if you're listening, you might be thinking, wait, couldn't the model just be overfitting to the JSON syntax?
Yeah, like maybe it just loves brackets and quotes, but isn't actually learning better visual generation. I would totally ask that.
It's a fair question, but they answered it through a massive controlled training sweep. They held architecture, compute, and initialization fixed.
Okay.
And this is where they found the scaling law. The converged diffusion loss is perfectly predicted by these information metrics, GPG and EV, not token count and not the JSON format.
Wow. So when natural language gets longer, token count goes up, but GPG and ED barely move, and loss stalls.
Right. But add SP fields, GPG and ED spike, and loss drops. It's a linear function of GPG with a Pearson correlation of negative 0.984.
That is insane.
And it follows a power law with ED, correlation negative 0.971.
It proves visual generation is bottlenecked by prompt information density, not model size. But okay, let's talk usability. Because the average user is never going to write a 1,300 token JSON file to generate a picture of a dog on a skateboard.
No, absolutely not. So the researchers framed this as promptability. To bridge the gap, they trained a dedicated LLM prompter.
Right, an LLM that takes a messy user prompt and infers all the plausible visual details to build that massive JSON.
Exactly. And the training pipeline for this LLM has 3 stages. Stage 1 is SFT, supervised fine-tuning, just teaching it the target SP distribution.
The basic JSON schema? That makes sense. Stage 2 is cold start bootstrapping, right?
Yeah, so they create prompt-to-chain of thought to SP derivations from those privileged image condition traces we mentioned earlier.
but without the LLM seeing the actual image, so it has to rely on spatial reasoning.
Right, it literally writes out its logic. Like, if a dog is on a skateboard, the dog's bounding box must sit above and intersect the skateboard's bounding box.
It reasons through the physics before outputting JSON. That is wild. And stage 3 is RFT via OPSD.
Yeah, reinforcement fine-tuning via on-policy self-distillation. The student LLM generates its own rollouts.
Its own attempts at structured prompts.
Right. And an ED-inspired QA verifier acts as a gatekeeper. If the rollout makes spatial sense, an image-conditioned teacher provides the optimal target.
And the diffuser itself is kept totally frozen during all of this, right? They only update the LLM prompter.
Exactly. And because the prompt engine is separate, they unlock a crazy inference-time feature, the agentic refine render judge loop.
This is so cool. Normally, if a model messes up and gives you a hovering coffee cup, you just have to re-roll the whole prompt and pray.
Right. Standard one-shot generation.
Yeah.
But here, a multimodal judge inspects the output. If it sees a hovering cup, it doesn't scrap the prompt.
It iteratively revises just the specific SP fields that failed, like the depth value of the cup, then re-renders.
It's literally targeted debugging for image generation.
Unbelievable. So what happens when we unleash this end-to-end system on the benchmarks?
It dominates. It outperforms the evaluated open-weight models, like Qwen-Image, which was their baseline, on nearly every compositional and reasoning benchmark.
And it matches the strongest closed-weight systems just by changing the text conditioning architecture.
Yep, but honestly, the killer feature here is zero-shot editing.
Yes, this is massive. Because all the visual factors are exposed as editable JSON fields, you can do targeted edits without extra training.
Right, so imagine an AI image of a study desk with blue ballpoint pens. Normally, if you prompt it to change to brass fountain pens, the text encoder blurs everything.
It might accidentally move the coffee cup or change the lighting entirely just to accommodate the new pens.
Exactly. But with the structured prompt, you just locate element6.material in the JSON. You swap the string from blue ballpoint to brass fountain pen.
You leave the bounding box alone. You leave everything else alone, and the diffuser just updates the pen.
Exactly. Or change scene.setting to rainy night cafe in style to cyberpunk neon noir.
It updates the global vibe while keeping the exact spatial layout of your books and cup. It's basically like having the DOM, the document object model for an image.
That is a brilliant analogy. You aren't repainting the canvas blindly. You're just updating the CSS for a specific div block.
It turns image generation from an unpredictable art form into structured engineering.
Yeah, they separated content from presentation and geometry from semantics.
Okay, so to wrap this all up, we've seen how unstructured prose hits an information ceiling, and how structured JSON forces diffusers to learn discrete variables.
And we looked at the math proving the scaling law with GPG and ED metrics, plus the LLM Prompter pipeline.
But I want to leave you with a broader implication to chew on today. If text conditioning for images was fundamentally bottlenecked by the unstructured nature of prose, what does this mean for other modalities?
Oh, that's a great point.
Right, like are audio generators, 3D asset models, and huge text-to-video systems hitting artificial ceilings just because we are stubbornly feeding them messy natural language?
It's highly likely.
What happens when we stop treating these models like poets who need to be coaxed and start giving them structured semantic graphs? If verbosity isn't visibility, maybe it's time we stop talking to our models and start programming them.
Absolutely.
Thank you for tuning in to this deep dive on AI paper slop. Keep building, keep questioning, and we'll see you on the next one.